You have an optimization problem. You want to minimize a scalar-valued loss function j that is constrained by a linear system of equations. The optimization is not over x, but over some parameter vector theta that also affects the linear system of equations. You are now interested in the sensitivity or the gradient with respect to theta for some optimization algorithms. But how do you obtain it? In this video, we want to again look at the adjoint method for a linear system of equations, but from the Lagrangian point of view. Hi and welcome to this new video that will extend your knowledge of the adjoint method for a linear system of equations, because here we will look at a different perspective by using the Lagrangian of an optimization problem. So what we will be doing here is similar to the previous video. So it's similar to the sensitivity analysis by the adjoint method of the dj by d theta, which we did by the help of implicit differentiation. Here we don't need implicit differentiation, and in the end we will arrive at the same equations as we did in the previous video. Let us again highlight that the constraint that we have here is an implicit relation for j. So this is an implicit relation, and just to also refresh your mind here, this arises, for instance, when you discretize PDEs. So for instance, when you have a discrete PDE, for instance, if you simulate fluid flow or structural mechanics, and then throughout the process of setting up the system matrix and the right-hand side, you might involve some parameters which are collected in this theta vector. And the quantities that appear here have the following dimensionality. So we have j, which is a scalar-valued loss function. It has the explicit dependency on x and explicit dependency on theta. And since x is the solution to this linear system, it also has an implicit dependency on theta. The theta vector is the collection of the parameters. Let's say it's p-dimensional and real. Then we have the x, which is the solution to the linear system. Let's say it is n-dimensional, and let also our system matrix be a square matrix n by n. And the right-hand side is then also an n-dimensional vector. Essentially, what we have as the optimization problem is an equality constraint optimization. So we have an equality constraint optimization. And whenever we have equality constraint optimizations, we can easily solve them by the help of the Lagrange multipliers, which involves building a Lagrangian. And this Lagrangian then yields an unconstrained optimization, which we can more easily solve. So an unconstrained optimization. Then let us recall, how do we build the Lagrangian? So the Lagrangian will be similar to the target function. So it will have the dependency on x and theta. So we have our dependency on x, and then also we have our parameters optionally. And additionally, we get a Lagrange multiplier, lambda, and it is given as the original target function j on x and optionally on theta, plus lambda transpose, or the scalar product in essence. And then we take our equality constraint and rearrange for 0. So let's bring the left-hand side of the equation to the right-hand side. And then essentially we're getting b minus ax. And now, instead of taking the derivative of j with respect to theta, we will take the derivative of L with respect to theta. So we will have dl by d theta. And also remind yourself that is the total derivative. So we are interested in all the nested dependencies of our quantity. So we will have an x, which has a further dependency on theta. The Lagrange multiplier does not have any nested dependencies. It is just a multiplier. And then we have the explicit dependency. So we first have the partial j partial x. So dj by dx. And then total x by total theta. So we have propagated our derivative here. Then we also have to account for the potential explicit dependency of the loss function on j. So plus partial j partial theta. And then we go to the second summand here. As said, lambda does not depend on theta, so we can ignore it. So we get a lambda transpose and then opening brackets. And then first we have a total b total theta, and then minus opening brackets. And since a as well as x will depend on theta, we have to apply the product rule. So we will get first total a total theta times x plus a times total x total theta and then twice closing bracket. Let us look again at the dimensionality of our derivatives. So we have a dx by d theta. So x is n-dimensional, and then this Jacobian, because we have a vector with respect to vector, yielding a Jacobian, will be n by p-dimensional. Then we have the gradient of our original target with respect to f. This one will be a 1 by n-dimensional quantity. So in essence, this means it is a row vector. So again, let me quickly remind yourself that here, because it simplifies the multivariate chain rule, we will use the definition that the gradient is a row vector. So here, the gradient is a row vector, as we also did this in the previous video. And of course, the reason for this is that if we then do the matrix multiplication here, then the n cancels with the n, and we have a 1 by p-dimensional quantity, which is the dimensionality of the derivative we are interested in, the Lagrangian with respect to theta. Then partial j partial theta will also be 1 by p-dimensional. Then dB by d theta will of course be n by p-dimensional. Here we have dA by d theta, which will be n by p. And then here we have an n-dimensional quantity, our x. Then we have here our a, which is an n by n-dimensional quantity. And here we have our n by p dimension. And you here see that dimensionalities do not match in a matrix multiplication. We can't multiply this tensor with a column vector. So take this some sort of as a loose derivation. So this is not fully correct. But I would say it's okay because it doesn't change the big concept of how the adjoint method works. In case you want to implement this, you have to use index notation in order to do correct tensor multiplication. Okay, but we see that the quantity that has to come out of these matrix multiplications is then n by p dimensional, because n cancels with n here. So similar to the total b total theta. And then our Lagrange multiplier has to be, of course, 1 by n dimensional. So this one will be 1 by n dimensional. That's because we transpose it so that we get a row vector. And then also by matrix multiplication, the innermost dimensions cancel and we get 1 by p, which is the quantity we're interested in. Okay, now we have the Lagrangian, and inside of this Lagrangian, we have a really difficult quantity. And these are this one here and this one over there. So these are difficult. But why are they difficult? So this is the total derivative of the solution to the linear system with respect to the parameters that are involved in building this linear system. And in the video on the implicit derivation, we investigated this further and figured out that performing or getting this quantity explicitly scales linearly in the number of parameters that are involved. And that's a problem because we want to solve scenarios where we have 100,000 parameters, and if something scales linearly in the number of parameters, this might render the solution to this problem infeasible. So we want to find the adjoint method, which only takes 2 solutions to the linear system, as we will see in the end. So we somehow have to get rid of this quantity. And in order to do this, let me rearrange this equation a little bit differently. So I will say some rearrangement. We still have the total derivative of the Lagrangian with respect to theta. And we first have partial j partial theta, then plus lambda transpose of dB by d theta, which is this quantity. It does not involve any dx by d theta, as well as this quantity. So we can have minus dA by d theta times x. And again, that's the quantity where you need to use index notation for. And then we close it down. And then we have plus opening bracket partial j partial x minus lambda transpose a times dx by d theta. And that was our difficult quantity. And now we have it somehow isolated and we have a coefficient in front of it. And hypothetically, if this quantity was 0, or in this case more precisely it is the 0 row vector, then we wouldn't have to calculate this quantity because 0 times something yields 0. So is there a way to make this 0? So that's our goal. We want to make this 0. And that's actually doable because here we have our Lagrange multiplier inside. And the Lagrange multiplier is arbitrary. So because lambda is some sort of arbitrary in the optimization problem that we want to solve, this is a condition for finding the minimum. So this condition has to be always true when we want to have our legit constrained minimum. So in essence, when we build the Lagrangian, this will always be 0. So the Lagrange multiplier is just a concept to help us find the constrained minimum. So here we want to use it in a way that we select it such that this part becomes 0 and we don't have to evaluate this one here. And this gives rise to the adjoint system. So then we get the adjoint system, and the adjoint system will then be dj by dx, or partial j partial x, minus lambda transpose times a is 0, or more precisely, the 0 vector. Then let's rearrange this for lambda. So we first get a lambda transpose times a is dj by dx, and then we can apply the transposition on both, and this gets us lambda transpose times a in brackets transpose is dj by dx in brackets transpose, and let's apply the transposition so it changes the order. We have an a transpose times lambda times dj by dx in brackets transpose, and bingo, that's the same adjoint system as we've also found in the video with the implicit differentiation. And once we have a solution for lambda, we can plug this back in here, this was 0, and we can evaluate the derivative of the Lagrangian with respect to theta. And as a remark, the system is really close to what we have up here. We have almost the same system matrix. It's just a matrix transpose. And that's the reason why for real valued matrices, the transpose is also called the adjoint of the matrix. So this one is the adjoint of A, and then it makes up the adjoint system of equations. And then once we have the lambda, we can get our required gradient, which was the Lagrangian with respect to theta, as partial j partial theta plus lambda transpose, and then opening brackets, dB by d theta in a total sense, minus dA by d theta in the total sense, times x, and then closing brackets. And the lambda, as said, is the one given by the adjoint system. And et voila, now we have the expression of finding the total derivative of the Lagrangian with respect to theta. But wait a minute. If we go back up, we see that our actual goal was to find dj by d theta. We either want to use this for gradient-based optimization, or we just want to look at the local sensitivities. So let's note this down, saying, but we wanted actually dj by d theta, so total j by d theta, not dl by d theta, which was the Lagrangian. And that's not a problem because they are identical. Why is that? Recall the definition of the Lagrangian for our equality constraint optimization. So we said L is J plus lambda transpose times B minus AX. And this B minus AX will always be 0 because that's a fixed constraint that we have to adhere to. That's also the reason why we were allowed to choose the lambda. So this has to be 0, or more precisely the 0 vector. And then its derivative is 0. So hence its derivative is 0. Because you have to think of L as a nested function of theta. And whatever theta you choose, this equation or this linear system will always be 0 because it defines how we get the x, because the x is the solution to this linear system. And due to the fact that at every theta that we could potentially choose, this is 0, we also do not have any change in the value. So when a function is 0 everywhere, then its derivative is also 0 everywhere. And by this, we can say that dl by d theta is equal to dj by d theta. So then we have that dl, or total L by total theta, is total j by total theta. And so whenever we evaluate the derivative of a Lagrangian, we also have the derivative of the target function. Then let us summarize again the strategy for getting the dj by d theta. And for this, we first solve forward, and we solve the linear system of equations axb for x. And then we solve the adjoint system, which was A transpose using the adjoint of our matrix times lambda is dj by dx in brackets transpose, and I use a transposition due to the fact that we defined gradients as row vectors. And then point number 3, we need to evaluate the following expression yielding dj by d theta, the quantity we're interested in, being partial j partial theta plus our lambda transpose times db by d theta in the total sense minus dA by d theta in the total sense times the vector x, and we plug in the values lambda here and the x here, and I should also indicate that we solve the linear system for lambda. And then closing the loop, here we have two solutions of a linear system, and they are of identical complexity because the transpose of a matrix has the same shape as the original matrix. So we have we have a solution forward, a solution backwards, and a little bit of overhead. And then it scales constantly in the number of parameters. So even if we have 100,000 parameters in our parameter vector or 1,000,000 parameters in our parameter vector, we only need to solve the system twice. Whereas for the naive approach, for the forward sensitivity analysis, we would have needed 1,000,000 solves of the system. And similar to the video with implicit differentiation, we still have some derivatives left. So the dj by x, dj by theta, and then these two total derivatives. However, if the upstream or downstream definitions of b, j, and a are given by explicit forward computations, we can just simply use automatic differentiation to obtain them, and maybe even simplify this multiplication of lambda with the respective derivatives to be even more computationally efficient, but that's the topic for another video. If you have any questions to this Lagrangian point of view derivation, then please leave a comment, and also check out the more detailed video with the derivation by the implicit derivative. If you enjoyed this video, then also consider liking and subscribing. I would appreciate this. Here you will now see similar videos, and I hope to see you next time.